In the beginning, there was darkness, and then bang, giving birth to an endless expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. Among the swirling gas and dust in the arms of the Milky Way, stars flash into existence, not alone, but in clusters, held together by the force of gravity.
Gravity is like the sculptor of the universe.
Now, take a grand tour of the galaxy's star clusters, the treasure maps of space, holding critical clues to the mysteries of the Milky Way's 400 billion suns.
Star clusters really allowed us to get a handle on how stars go through their lives, how they live and die.
It's a violent, chaotic existence, where our search for cosmic clusters may end up revealing a universe in darkness for eternity. About 1,000 stars are visible to the naked eye during a dark night on planet Earth. While the glistening display may impress us, there are places in the galaxy where the view would blow us away. Imagine the sun on the edge of a giant cluster made up of 1 million other suns, filling the heavens horizon to horizon.
The stellar density is really high. The distances between stars can be just a few hundredths of a light year, something like that.
The galaxy's magnificent clusters are more than just beautiful to look at. You may not realize it, but they hold the very secrets to the way stars are created and how they're destroyed in massive supernova explosions that generate the very elements of life. Our search for cosmic clusters begins not through the eyepiece of a telescope, but in the cockpit of an interstellar spacecraft. Our mission? To traverse the galaxy and find out why clusters are so valuable. Why they are keys to unlocking the mysteries of the stars. Our first stop? The Pleiades, the most famous star cluster of all. 440 light-years from Earth. Known since antiquity, it contains 1,000 stars, though only a handful can be seen from Earth.
The Pleiades are the so-called Seven Sisters, a bright, easily noticeable grouping of stars in the winter skies. Well, it turns out only 6 of the stars are easily visible. You can see 6, and really sharp-eyed people can see 8 or 9 or 10. Rarely have I met anyone who can see precisely 7 stars. So maybe in antiquity, there was a star that was considerably brighter than it is now, but it has faded since then, so now there are only 6 easily visible stars. There are actually hundreds of stars in the Pleiades, perhaps up to 1,000.
We circle the Pleiades in search of clues that can reveal the secrets of the universe, because clusters hold the key to understanding how stars are born, how they live and die, the secrets of creation. Like all clusters, we see that the stars in the Pleiades are so close to each other, they are all virtually the same distance from Earth.
Of course, the stars in a cluster are not all exactly at the same distance from us, but they're so far away that the slight differences in distance are really pretty small. They're inconsequential. A nice analogy is viewing a stadium full of people from a blimp high above. From the perspective of the blimp, most of the people are at about the same distance.
Most of what we know about stars, their size, weight, and age, comes from figuring out their inherent brightness. But you can't judge a star's true brightness without knowing how far away it is. That's where the cluster comes in.
The fact that all stars in a star cluster are basically the same distance from us is very important. It gives us a sample of stars where we can actually see what the intrinsic, real brightness of these stars are. Unless we know these stars are all at the same location, we don't know whether we're looking at a bright star that's far away or a dimmer star that's close to us. There's no way to tell. But in a cluster, all together, you can see that.
The same rules that apply to stars in the sky also apply to cars on the road.
What we have here are two cars, same make, same model, so we know the headlights on each car are exactly alike and equally bright.
From where I'm standing here, one car's headlights look just like the other. That makes sense. But now, let's make these cars act like stars in the universe. Same stars, but at different distances. Okay, Amy, back it up. Look at these headlights now. The ones over there are much dimmer than the ones here, even though we know they're the same. This is the inverse square law. If that car is twice as far away, then the headlights are 4 times dimmer. If it's 4 times farther away, the headlights are 16 times dimmer, and so on as far as you care to go.
But sometimes a light that appears to be dimmer actually is.
This flashlight and the headlights are just like stars in a star cluster. The flashlight next to the headlight looks dimmer, and that's because it is dimmer, not because it's farther away. A dim star next to a bright star in a cluster looks dimmer because the star itself is dimmer, not because it's farther away.
Up close, we see the Pleiades has a mix of bright stars and dim stars. And it's this very variety of different stars in a cluster, all in the same place, that solves the puzzle of stellar evolution.
Star clusters really allowed us to get a handle on how stars go through their lives, how they live and die. Think of it this way. If an alien wanted to learn how humans live and die, but they could only watch us for 30 seconds, they flew by Earth, and they took pictures of millions of humans. Even though they couldn't watch a single human live and die, as a group they could piece together our story. They looked at some babies, they looked at older people. A star cluster is just that. It's a single snapshot in time, but there are stars at every different part of their lives, and that was the tool astronomers needed to piece together what a stellar lifetime is like.
We know that the biggest, brightest stars are the most dangerous, so we keep our distance. These are the live hard, die young stars of the universe. Those that expand to giant size before going supernova. The dangers lurk even in clusters with appealing names, like the Jewel Box. But the next stop on our journey is a place in the sky very familiar to people in the Northern Hemisphere. We are 80 light years from Earth, approaching the closest cluster to our planet, the Ursa Major Moving Group. As we bring our starship around, we see 5 of the central stars in Ursa Major form what we know as the Big Dipper.
People noticed that they actually move across the sky together. With most constellations, the stars, even though they look like they're part of the same constellation, they're actually completely unrelated to each other. They have nothing to do with each other gravitationally. However, the stars in the Ursa Major Moving Group actually formed at the same time and are part of the same moving group.
In time, the movement will change the appearance of the familiar pattern of stars. We're visiting Ursa Major to explore another cluster question. Why are some more spread out than others? Irregular in shape and scattered in appearance, they're called open clusters.
An open star cluster is a relatively loosely bound aggregation of stars. They form in the spiral arms of a spiral galaxy, and then they gradually move away, and then they disperse.
Scientists believe virtually all stars are born in clusters. But as time goes on, the stars in open clusters get scattered apart by the gravity of other passing stars. That means most clusters are young, because otherwise, their stars would no longer be in clusters.
A star cluster is kind of like this pile of confetti on my hand. Gravity gradually pulls the stars away and disperses the cluster. Well, I can blow on this pile of confetti and disperse the pile. Let's do it. Now, if this were a star cluster instead of a pile of confetti, then gravity would be the agent that gradually pulls the stars away, dispersing the cluster over time until there's little, if anything, left.
As explorers, these young clusters are important to us. With a lot of stars in one place, it's as if we can take a poll and figure out how common or rare different kinds of stars are in the galaxy. In most clusters, we see quickly that there are a few very big bright stars, maybe a larger number of ordinary stars, like our Sun, and lots of small, dim stars, barely visible in the crowd. But how crowded are they, really? Stars in clusters are many billions of miles apart. But when we add up their distances in our Starship computer, we find they're much closer together than we're used to at home. The density of stars in the Sun's neighborhood is little more than 1 star for every 50 cubic light years. In a typical open cluster, there would be 500 stars in the same space.
We were once in an open cluster, but we've been around the galaxy so many times now that our sister stars may be all the way on the other side of the Milky Way.
What would it have been like for the Sun when it was part of a cluster? To find out, we file a flight plan for a place where stars are forming in a cluster right now. We're headed 1,500 light years from Earth to the Orion Nebula, which looks like a fuzzy star in Orion's sword. Up close, though, it's a spectacular light show.
The Orion Nebula is one of the great stellar nurseries that we know of. It's forming stars right now. And if you were to fly through the Orion Nebula, you would see a whole bunch of stars, but near the middle, there are 4 particularly bright stars. They form a configuration called the trapezium. And if you were to fly past these stars, you would see these 4 newly formed, brilliant stars and a whole bunch of little guys all floating around. It would be a wonderful journey.
We head toward the trapezium stars, the 4 brightest in a cluster that's a hectic laboratory of star formation. Thousands of other stars have formed or are in the process of forming. But as it's happening, scientists believe the cluster is imposing a kind of birth control on the whole cycle.
Only about 10% of the mass of a cloud which will form stars actually becomes stars. So why is it that so little of the matter in a cloud actually turns into stars? What we've come to believe now is that there may be a feedback process. So once you form stars, they feed back on the cloud, acting like a thermostat and actually limiting the amount of star formation that can form. In the trapezium cluster, you've got those 4 massive stars that are producing enormous amount of ultraviolet radiation, as well as winds that stream into the surrounding area, and they will affect the gas that wants to form stars. So even though you have another 1,000 stars forming around the trapezium, the star formation rate in that area is being affected by the ultraviolet radiation and the winds from those massive stars.
If nebulas are the stellar nurseries of the cosmos, then clusters are their grade schools, where stars stay together until life and the galaxy drives them apart. But it's clear not all clusters are alike. We're due now to encounter clusters that make up some of the most extreme environments in the entire galaxy, where stars are so massive they are on the verge of blasting themselves into oblivion. When it comes to star clusters, one of the first things most people want to know is, what's the biggest? Which ones really stand out? It's no different than looking at a big city. You want to know about its tallest buildings, its most distinctive landmarks. If there's an Empire State Building of star clusters, we'd have to travel 10,000 light years to find it. It's called Westerlund 1, a supercluster with a total mass 100,000 times our Sun.
Westerlund 1 right now holds the world's record for the biggest known young cluster. It has about 100,000 stars, and what's really odd is for a long time we didn't even know it was that massive. Astronomers have known about Westerlund 1 for a long time, but only about 5 years ago did we first get a glimpse of all the stars in the cluster, because that's when we had infrared detectors that could peer through the dust in the galaxy that's situated between the Earth and the cluster.
Recent advances in infrared astronomy revealed a space only 6 light-years across, packed with a thick population of stars. The biggest and brightest are galactic freaks, supergiant stars, in a range of sizes and colors from blue to red and even yellow.
The blue supergiant phase and the yellow and red supergiant phase represent phases during the lifetime of a massive star. They start blue, they become red. In some cases, they go back and forth between blue and red as the outer layers are lifted and we see deeper to the hotter material. In between the red and the blue phases, they're yellow, and so we call them yellow supergiants.
The Sun, which so often is called an ordinary star, is tiny when compared to supergiants of any color.
Suppose our Sun, which is over 100 times the diameter of the Earth, were scaled down to the size of this little yellow pinhead here, less than 1/8 of an inch in diameter. So we're really scaling down the Sun a lot. In that case, the largest stars, the red supergiants, would be about the size of this telescope dome behind me. They're huge compared with the Sun, and yet the Sun itself is already huge compared with the Earth.
Supergiant stars, whether blue, yellow, or red, are collectively called evolved massive stars. That means they've burnt out their nuclear hydrogen fuel and are transforming into giants that may eventually explode as supernovas. Supernovas are so bright it's easy to see them from great distances. But David Y. from Wing, Pennsylvania wants to ask the universe if a supernova can cause space and time to warp enough to make us notice a change.
David, we sure hope that a supernova will create a big enough disturbance, a warping in space and time, to be noticeable. But it won't be easily noticeable. You won't be jostled around. But we hope that the current and future generation of gravitational wave detectors will detect these slight ripples in the fabric of space and time. That's the new unexplored window of astrophysics, gravitational wave astronomy.
Our own Sun will evolve into a red giant. It will expand enough to engulf Earth's orbit, but it won't reach the size of Jupiter's orbit like supergiants, and it won't explode in a supernova. Having supergiants in a cluster gives us clues to the cluster's age.
Now, those incredibly massive stars are important because they have very short lives. They only live for maybe 5 or 6 million years. So if you see a star, a massive star that's evolved, it's near the end of its life, you know that the cluster can't be more than 5 or 6 million years old. Because if it were, that massive star would already have blown up.
To date, astronomers have discovered only a handful of these extremely massive clusters. And like Westerlund 1, all of them were virtually unknown until very recently.
Just to express how ignorant we are, realize that only 10 years ago, we didn't know about any of these massive clusters. Every young cluster we knew about, more than 10 years ago, all had less than 10,000 stars. We know of thousands of those kinds of smaller clusters. Right now, we only know of a dozen of the massive clusters.
Because our galaxy is so filled with dust, most star clusters discovered so far exist in an area surrounding our particular place in the Milky Way. We can see barely as far as the center of the galaxy. But as technology improves, our view will extend further and further into the more distant spiral arms.
Westerlund 1 won't be the most massive young cluster known for a long time. We're still discovering these other clusters all the time.
A few superclusters are near the galactic core, where the gravitational tides of the Milky Way's giant black hole may rip them apart in just a few million years. For now, though, their massive bright stars are being studied intensely. Our next stop is the quintuplet cluster, a massive 4-million-year-old cluster named for 5 supergiants dominating its center. It is also home to the Pistol Star, one of the brightest stars in the entire galaxy. The cluster has 5 mysterious supergiants whose secrets are shrouded by red dust clouds. In 2006, puzzled scientists tried to get a closer look at them. Using the Keck telescope in Hawaii, what they found was startling. 2 of the stars are surrounded by bizarre spirals, which means the supergiants are not alone.
In the quintuplet star cluster, there are several massive stars that are in fact in binary systems, and they're in the process of gently blowing away their outer envelopes. And those envelopes are colliding and forming this spiral pattern. It's very unusual to find several of these things in the same place. Such stars are very rare. If you look elsewhere in our galaxy, you'll find one every once in a while here and there, but not several of them in one concentrated location.
It's only a matter of time before these and any of 100 other supermassive stars light up the cluster with supernova explosions, blowing away their own planets and wiping out any civilizations on neighboring worlds with deadly radiation. Similar dangers lurk inside another cluster close to the galactic center. It's called the Arches Cluster, 25,000 light-years from Earth and just 100 light-years from the Milky Way's core.
The Arches Cluster was the first young massive cluster discovered in the galaxy. It is the densest young cluster in the galaxy.
Our own sun's neighborhood is practically empty compared to the Arches Cluster. In the 50 cubic light-years around the sun, the only neighbor is the Alpha Centauri system. If we were in the Arches Cluster, the stars are so tightly packed, this same space would contain more than 1 million stars, lighting up the sky of any planet both night and day.
If we lived on a planet surrounding a star in the Arches Cluster or a cluster that's similarly dense, we would see thousands of stars in the night sky. In fact, some of those stars would be so bright that they would individually be much brighter than the full moon. The night sky would be very bright. It would be comparable to the light level in an office during the day.
The Arches Cluster is a major landmark in our galaxy because it was used by scientists to figure out just how big a star can get. Our search for cosmic clusters has taken us to the Arches, one of the most important clusters in our galaxy. It's here that scientists discovered just how massive a star can get.
That seems like a simple question, but we didn't know up until a few years ago how massive a star could actually be.
The Arches had everything scientists needed to answer this question. First, in such a big cluster, there were surely many massive stars to study. Second, at roughly 2.5 million years old, the cluster was young enough that its massive stars wouldn't have exploded yet. So the biggest star in the cluster would probably be a good guide for how massive stars can get in the wider universe.
What we saw in the Arches is a collection of many, many low-mass stars, not so many, maybe hundreds of medium-sized stars, and then a dozen or so very massive stars with 130 times the mass of the sun in them. Beyond that, we saw nothing. It was like falling off a cliff. If stars more massive than about 130 solar masses can form and live, then they would have been there in the Arches. So apparently, nature has placed a limit on the maximum mass of a star. It's probably somewhere between 130 and 150 solar masses.
As we travel away from the very young Arches Cluster, we chart a course for a very different part of the galaxy. Out in the Milky Way's quiet suburbs are its senior citizens, the globular clusters.
A globular cluster sounds so wonderful. It's one of my favorite words, a glob, and that's exactly what it is. Often up to 1 million stars in a tight, large cluster. These things are really mysterious because they seem to be very old, some of the oldest stars in the galaxy. In fact, some of the stars are so old, they're practically as old as the universe itself.
Though they are visually stunning, it's the age of the globular clusters that makes them so exciting. Since they are nearly as old as the universe itself, they raise the question of the galaxy's age. Is the Milky Way as ancient as the universe itself?
We have good evidence that the universe is about 13.7 billion years old. Given that the oldest globular clusters are about 13 billion years old, this means that they formed within the first billion years after the Big Bang. This essentially marks the birth of our galaxy, and we think other galaxies as well, in many cases, were formed within the first billion years after the birth of the universe.
Scientists don't know how globular clusters form. It's one of today's enduring mysteries of astronomy. Because they are found in other galaxies too, it may have something to do with galaxy formation itself.
Because we see that individual stars and globular clusters are very old, in some cases being dated to 13 billion years old, we know that the globulars are that old, and we know that they were formed right at the time when the galaxy was forming. It's still unclear whether the system formed first and then the galaxy condensed out of the remaining molecular cloud, or if they condensed and collapsed and formed at the same time.
Finding globular clusters takes us outside the chaotic disk of the galaxy, where most of the stars reside, and to a place called the galactic halo.
The halo of our Milky Way galaxy is a vast, roughly spherically shaped distribution of stars that's around, it envelops the disk of our spiral galaxy. It's where the globular clusters live.
There are about 160 globular clusters now known, but it's believed there were once many more of them. Their presence in the halo, outside the influence of the galactic disk, may figure into the way they keep their spherical form. It may be that any globulars near the disk dissipated long ago. But there's at least one cluster out in the halo that's in danger of being ripped apart. A cluster that has lost 80% of the stars it had when it was first formed. We set our course for globular cluster M12 to get an up-close view of the devastation.
M12, instead of orbiting outside of our galaxy or going through the outer edges, actually passed close to the center of our galaxy. And when it did that, the gravitational interaction with all the other stars inside the Milky Way was strong enough to pull off some of the low-mass stars inside the cluster. So what's happening is that M12 is slowly losing its lowest mass stars with every successive passage through our galaxy. And eventually, there's not going to be anything left because it will have been completely devoured by the Milky Way.
For now, most globular clusters remain very crowded. 60,000 times as dense in stars as our own galactic neighborhood. But because the clusters are old, any massive bright stars they once had have long since burned out. The globular cluster sky would be crowded, but its glow would remain subtle.
If we were on a planet around a star in a globular cluster, we would see thousands of stars, but the average illumination at night would be comparable to the illumination you'd experience in a room with some candles lit up.
Orbiting out in the halo, globular clusters are to the galaxy something like moons are to a planet. Globular clusters on the outskirts of other galaxies show that this is something many galaxies have in common. Now, our route through space takes us far outside our own galaxy. 60 million light-years away to a massive elliptical galaxy called M87 that looks something like a globular cluster itself. Most of the fuzzy dots in this photo from the Hubble Space Telescope are globular clusters orbiting M87. The giant galaxy has 15,000 of them. But M87 represents the upper end of the clustering phenomenon. It sits at the core of a cluster, not of stars, but of galaxies, where our starship now travels to witness the violence of giant star systems colliding at speeds of 1,000,000 miles an hour. All it takes is a few quick looks at star clusters to see how obvious gravity's effect is in holding stars together.
Gravity is like the sculptor of the universe. It influences large regions around it. So it can cause galaxies to cluster together just like stars cluster together, but on a much, much bigger scale, on scales of millions of light years. That's fantastic.
It's a process that begins right in our own astronomical backyard, where our spaceship prepares to fly outside the galaxy.
The Milky Way is a largish but relatively typical spiral galaxy, and we're located in a small galaxy group, which is a very typical kind of environment for material to be located in the universe. Only about 5% of galaxies are located in rich clusters, but more than half of them are located in small groups of galaxies.
Our galaxy's home cluster is called the local group. A trip across 3 million light years takes us past its two big members, the Milky Way and M31, the Andromeda Galaxy. The Triangulum Galaxy is the next largest, and a few dozen dwarf galaxies circulate among them.
The galaxies within an individual cluster tend to gradually merge with time. So in the next 4, 5, 6 billion years, our Milky Way galaxy is going to merge with the Andromeda Galaxy.
Right now, if we view the whole universe from Earth orbit, our view screen looks like this. Our own galaxy's plane dominates, stretching across the center. But when we merge with Andromeda, the sky will look vastly changed.
And a very spectacular event, it's likely to result in an elliptical galaxy, which looks very, very different than either of the two component spirals.
Andromeda will fly by several times, as it and the Milky Way do a gravitational dance. The merger will destroy their elegant disk shapes. In the end, they'll settle into a giant rounded blob, the typical form of elliptical galaxies across the universe. The local group is tiny compared to the big galaxy clusters across the universe. The nearest big cluster is the next stop on our voyage.
Our local group is about 60 million light years away from a much bigger cluster, the Virgo cluster of galaxies, consisting of thousands of galaxies, not just a few dozen. And our local group in the Virgo cluster and a bunch of other clusters are part of an even bigger structure called the local supercluster.
Such clusters are violent places, with galaxies moving at incredible speed.
We're talking about speeds of hundreds of kilometers per second, or another way of saying that would be something in the vicinity of 1,000,000 miles an hour.
We take our trip into the high-velocity realm of these giant clusters to solve a mystery about galaxies. Why some have stars forming in clusters and others don't. The answer is found in galactic gas.
Galaxies are sometimes gas-rich and sometimes gas-poor. Gas-rich galaxies tend to be forming stars fairly actively, and the gas-poor ones don't.
It turns out that the action in galaxy clusters is something like a war zone, where the 1,000,000-mile-an-hour speeds put any gas-rich galaxy in danger of being strangled.
Galaxy strangulation occurs when a galaxy that's not part of a cluster comes close to a cluster, and the gravitational pull, the tidal pull of that cluster, can remove or suck gas out of that incoming galaxy. That leaves the galaxy deficient in gas, and so it's unable to form many new stars. It gets strangled.
And once a galaxy travels deep inside the cluster, it faces trouble from what's called ram pressure stripping, as it speeds through the thin gas floating in the cluster space.
When zooming through that gas, the pressure of the gas can actually strip gas away from the galaxy itself, leaving it relatively gas-free and unable to form many new star clusters.
If we flew through the cluster looking for the intergalactic gas, we wouldn't see it. It is so very thin that on Earth, we'd consider it a perfect vacuum. But if we turn on our spaceship's X-ray detectors, it would show up as a massive, eerie glow.
The galaxies that we see in visible light, if we look with an ordinary telescope, aren't the only component of galaxy clusters. Indeed, they're not even really the dominant component. The dominant component is a hot, thin gas. And the gas was heated by shocks during the formation process of the clusters, and is now so hot that it glows in X-rays. And this is completely invisible to normal light.
The hot gas exerts more gravitational influence on the cluster than the visible galaxies themselves. Its overwhelming gravity helps draw cluster galaxies to a common center. And when we look at galaxy clusters, we see a preview of our own future. In the cluster center is often a giant elliptical galaxy, the result of countless gravity-driven mergers, like the one that will join the Milky Way with Andromeda.
That's a common trend for clusters of galaxies. The galaxies within them are merging together, forming a few and finally one supergalaxy.
Is the universe destined to be filled with isolated supergalaxies? Will gravity continue its unending pull? To find the answers, we enlist supercomputers as time machines, taking us into the future. The scenario they predict may be far more grim than anyone ever suspected. The world's greatest telescopes and satellite observatories routinely serve up awesome pictures of cosmic clusters. But essentially, these are only snapshots in time. To truly watch the universe as it evolves, we need a time machine.
Human lives are short compared with cosmic timescales, but we can watch effectively how galaxies and galaxy clusters evolve by simulating them on powerful computers.
The supercomputer turns our starship into a time machine for the next leg of our mission, to find out how the universe evolved and where it's going to end up. This simulation shows how a galaxy cluster may form. 12.3 billion years of stellar evolution is condensed into less than a minute. Supercomputer visualizations like these are important tools to help all of us understand the workings of the universe and where the future will take us.
The simulations where we can actually play how a galaxy cluster evolves over billions of years always leave me breathless. It's amazing to watch cosmological time play in these beautiful, elegant simulations.
Here's how the supercomputers do it. They start with something that scientists call the N-body problem. N stands for the number of bodies. The bodies are planets, stars, or galaxies. And the problem is to do some simple math to figure out how Isaac Newton's basic laws of gravity make the planets or stars move in space.
Such simulations are remarkably powerful ways to study how complex systems like clusters of galaxies and galaxies evolve with time.
Peter Toobin, a simulation specialist at the University of Maryland, programs the gravity formulas into a supercomputer named Deep Thought. It's easy, for instance, to figure the orbit of a planet around a star. That's called a two-body problem. A college math student can do it in a snap. But suppose you have to work out the motions of a swarm of stars in a star cluster.
The n-body problem is a little bit like a juggling act. If you have a two-body problem, Here we have one ball. I can do one ball relatively easy, but I'm not a juggler. I don't know if I can two balls. Oops. Well, clearly I cannot do two balls. And it takes a lot of effort and interpretation by the brain how to correctly juggle two balls. Now imagine that we have to do three balls or four balls. I cannot do that. There are people who can do that, but the complexity ends at some point. Nobody can do 20 balls.
Surprisingly, the math behind the problem is fairly easy. But the reason you need a supercomputer is that there's just so much of it to do. It's pure grunt work.
All right, guys, ready your position.
As Tubin's students demonstrate when trying to do it for 12 stars without a computer.
Number 1 is at 6-4.
Number 2.
2 is at 3-4.
Number 3.
3 is at 2-4.
In calculations like these, each star's starting position gets coordinates on a chart.
Number 8 is at 4-4.
Each star also gets its own speed, and the rest is up to the students. Using Newton's laws, they have to figure out how each star's gravity acts on each one of the others to determine where each star's position will be at the next point in time.
Number 1.
These students would need to work for 300 years non-stop to do what a supercomputer can do in 1 second. Calculations for galaxy clusters ramp up to millions, even billions of n-bodies. But fortunately, supercomputers are increasingly available to astronomers, eager to simulate the past, present, and future of the universe.
The current state-of-the-art supercomputers are actually off-the-shelf computers that you and I use at home, desktop computers. The only thing is we put them all together. They're easy to build, they're cheap to build, so there's many available.
Among the most complex of the current simulations is the Millennium Run in Europe, where 10 billion galaxies were manipulated in a supercomputer running continuously for 28 days, utilizing 343,000 processor hours. One result is a remarkable 3D fly-through across 2.4 billion light-years of space, showing hundreds of millions of galaxies clumped together in clusters along vast strands of dark matter. Using supercomputers, scientists not only study the past, but they can predict the future of the universe.
I think it's amazingly cool that we can actually take what we know about the present-day conditions in the universe, and we can basically use these computer simulations to play time forward. We can use this to extrapolate what's going to happen to us in the end.
This simulation starts with the quantum foam left over from the Big Bang and flies us through 13 billion years as it all condenses into the galaxy clusters and superclusters along the network of filaments and voids, like those we can detect today. This is the cosmic clustering phenomenon, driven by gravity to its greatest extreme. But gravity's pull is counterbalanced by the mysterious dark energy that is driving the galaxy clusters of the universe apart.
About a decade ago, astronomers discovered that the universe is not just expanding. In fact, its expansion is accelerating with time.
Gravity will keep galaxy clusters together only on a local level. Our local galaxy group will coalesce into one super galaxy, but all other galaxies in the universe will race away from us. 100 billion years from now, this corner of space will be left virtually in the dark.
As soon as the distant galaxies around us will expand away and reach the speed of light, even light from them will never be able to reach us anymore. And so these galaxies will expand into vast regions of space and disappear from view. Our galaxy will be an island embedded in darkness.
Clouds of gas will continue to form into star clusters nearby, But astronomers of the future will see nothing in the sky beyond the borders of our own galaxy. Unless the work of today's cosmologists is preserved, there will be no clues to tell them that there was once a Big Bang and a cosmic expansion. Nothing to let them know of the vast existence beyond, the place we know today as the universe.